My name is Justin Lara. This is the Scenario 4 Running Rough assignment for Aviation 430 Multi-Engine Ground at Liberty University. In this scenario, I recently experienced some engine roughness on a flight. Because of this experience, I decided I should brush up on some one engine and operative procedures and operations. I will be discussing this topic with some fellow pilots at a club meeting in the not so distant future. I am not doing multi-engine training at the moment, so I don't have a multi-engine aircraft that I've been using, but for the sake of the scenario, I elected to use the Beechcraft Baron 58 like the one shown above. This graphic was taken from the Baron Pilot Operating Handbook and discussed some Vspeeds to use in emergency situations. The best angle of climb, Vx, for one engine in operative operations, also commonly referred to as VXZ, is 96 knots. This airspeed, according to the Pilot Operating Handbook, is used to only clear obstructions during initial climb out, as it gives the greatest altitude gain per unit of horizontal distance. It provides less engine cooling and requires more rudder control input than VYSE. The best rate of climb, Vy, for one engine in operative operations, also commonly referred to as VYSE, is 100 knots. VYSE is indicated by a blue line depicted on the airspeed indicator. It delivers the greatest gain in altitude in the shortest possible time. VYSE is based on the inoperative engine being in the minimum drag position, the operating engine at no more than max continuous power, the landing gear retracted, flaps up, cowl flaps as required for engine cooling, and the aircraft flowing at the proper bank angle, which I'll discuss more about later. Drag caused by a windmilling propeller, extending landing gear, or flaps in the landing position will severely degrade or destroy single engine climb performance. Since climb performance varies widely with type of airplane, weight, temperature, altitude, and airplane configuration, the climb gradient may be marginal or even negative under some conditions. VMCA or VMC is the one engine inoperative minimum controllable airspeed at sea level, which is 81 knots. It is designated by a red radial on the airspeed indicator. It is the minimum airspeed at which it is possible to recover directional control of the aircraft within 20 degrees heading change and thereafter maintaining straight flight with not more than 5 degrees of bank if one engine fails suddenly. We will discuss VMCA more thoroughly on a later slide. The one engine inoperative en route climb speed is 100 knots, and that makes sense because so is VYSE. The emergency descent speed is 152 knots. The one engine inoperative landing speed is 100 knots, with or without the use of flaps. VSSE, or intentional one engine inoperative speed, is 86 knots. It is the minimum speed at which to perform intentional engine cuts. Use of VSSE is intended to reduce the accident potential from loss of control after engine cuts at or near minimum control airspeed. VMCA demonstrations are necessary in training but should only be made at safe altitude above terrain with power reduction on one engine made at or above VSSE. VSSE provides a margin of error above VMCA. Finally, glidespeed, which should be used if both engines are inoperative, is 120 knots. When an engine fails in a multi-engine aircraft, the pilot experiences asymmetrical thrust. In order to counteract this effect, the pilot's flying handbook explains there are two control inputs that can be used, including yaw from the rudder and the horizontal component of lift from the ailerons. Manufacturers' performance charts have been determined given zero side slip. To ensure maximum performance is achieved with one engine inoperative, the pilot's use of these inputs should be done in a specific manner to make side slip zero. The rudder and aileron should be used together. With the proper combination of the two, the ball should be deflected approximately 1/2 to 1/3 toward the operative engine with a bank of about 2 degrees toward the operative engine. The actual bank angle for zero side slip varies among airplanes from 1 1/2 to 2 1/2 degrees, and the position of the ball varies from 1/3 to 1/2 of the ball width from the instrument center toward the operative engine. As the aircraft slows, control effectiveness decreases, requiring additional aileron and rudder input. When the aircraft gets to a speed in which full rudder and 5 degrees of bank can no longer counteract the asymmetrical thrust, The aircraft will begin to yaw uncontrollably toward the inoperative engine. The speed at which this occurs is VMC. If the pilot can no longer control the aircraft, they could regain control by reducing power and lowering the nose, then returning power to the proper setting once control has been regained. It is important to note that VMC is not a fixed airspeed under all conditions. VMC is fixed only at a specific set of circumstances under which it was determined during aircraft certification. The Airplane Flying Handbook describes various factors that affect VMC and settings required to be used by manufacturers when determining it. They must use maximum available takeoff power initially on each engine. VMC increases as power is increased on the operating engine. With normally aspirated engines, VMC is highest at takeoff power and sea level and decreases with altitude. All propeller controls must be in the recommended takeoff position throughout VMC determination because VMC increases with drag. The weight and center of gravity must be in the most unfavorable position that is allowed by the POH. VMC increases as the center of gravity is moved aft due to a reduced moment arm of the rudder. It also increases with an increase in weight. Landing gear must be retracted and flaps should be in the takeoff position, also due to the effects of drag. A maximum of 5 degrees of bank can be used. While unsafe to fly without using the rudder to stay coordinated, the decreased drag from the rudder allows for a decreased VMC. Other requirements include the aircraft is trimmed and is not experiencing ground effect. To correctly identify and verify, then feather and secure an inoperative engine, Doug Rosendahl teaches what he refers to as the drill. I like the way he teaches it because although it is not a mnemonic device or anything, it's got a rhythm to it and I've been able to remember the steps easily. The drill includes pitch for blue line, mixture, props, throttles, flaps, gear, identify, verify, feather, mixtures, engine failure checklists. The first step is to fly the plane and maintain control. The blue line is VYSE. We'll pitch for blue line if in a climb, but if we're in a cruise, then we should maintain an airspeed greater than VMC. Next, a pilot should deliberately push the mixture, props, and throttle forward in that order. The next step is to reduce drag by ensuring the flaps and gear are up, then securing the inoperative engine. If in cruise with plenty of altitude, the pilot may elect to try diagnosing and solving the problem before securing the engine. To secure the engine, the pilot must identify and verify which engine is inoperative. To identify, slap the dead leg or leg that does not have rudder pressure on it due to the corrections of the asymmetrical thrust. Identifying the engine can be done by verifying the engine can be done by slowly retarding the throttle of the inoperative engine. If there is a change in sound as a result of lowering the RPM, we have selected the wrong engine. We will then secure the engine by feathering the props and cutting off the mixture. Finally, we need to complete the applicable emergency checklists. These are the references I used to make my presentation. And again, my name is Justin Lara. Thank you for watching.